Okay, so now we're gonna start with question 3. Okay, so let's read the problem. A Japanese teapot has a hollow handle that feels cool to the touch even when a pot contains boiling water. This handle can be modeled as a hollow cylinder. Okay, so instead of a tapered cylinder like this, we will model this handle as a fin, but it's like a cylinder with a hole drilled through it. Okay, a hole, a cylinder with a cylindrical hole inside of it. Okay. Okay, so this problem is interesting. It doesn't have just one value of h. It has two values of h. See, outside, the convection has a corresponding coefficient of h naught, and then on the inside, the convection has a corresponding coefficient of hi. Okay, ho and hi. Yeah. Okay, so the handle is made of porcelain. And the thermal conductivity, so this is our K. So K is equal to 1.03. So calculate the appropriate parameter M of the hollow cylinder and show that this is a long fin. Okay, so a long fin refers to an infinitely long fin. Okay, you have to know that long fin, they're trying to imply that it is the infinitely long fin. This means infinitely long fin. Okay, now let me ask you this. Is the formula for this M square root of HP over KA? And the answer is no. Why? Because this was derived for a solid fin. Okay, this was derived for a fin that looks like this. But the problem is now we're dealing with, no, we're not dealing with this, but we're dealing with a fin that has a hole inside. Okay, and this changes the problem. Okay, so let me derive for you this one. Okay, and then we will apply that same idea and derive it for the this hollow fin. Okay, so what I'm gonna do is first I'm gonna derive the M for the normal fin, okay, to see how this comes about. Then I'm gonna apply the similar idea to find the M for the hollow fin. Okay, so let's have a look. Okay, so what is it? What I'm gonna do is let's consider a fin. So a fin looks like this, and then I'm gonna take an infinitesimally thin slice. Okay, so this slice is very, very, very tiny. Okay, but I just exaggerated a bit. Okay, so this is a infinitesimal slice. It's actually a very thin slice. Yeah, with a thickness of delta x. Okay, so let's zoom in a bit. So we zoom in. So let's see the heat transfer in this slice. There will be conduction going into the slice. So let's call this Q of x. Okay, don't forget we have a coordinate system. Okay, so this slice occurs at the position x. Okay, so this face occurs at x. Then this slice is delta x long. Okay, so that means this other face is at the position x plus dx. Therefore, the conduction through this face will be q x plus dx. Okay, then don't forget on this face, convection will occur. Okay, convection will occur. So q convection. Okay, so that's all our heat transfer in this. So we will consider the energy balance in this slice. Okay, so this slice is our control volume. And then, yeah, so let's go ahead and see what's the energy balance. So let's write out the full energy balance. So E in minus E out plus E gen is equal to E stored. Okay, now let's simplify. So there's no energy being generated, so this is 0. And then this is a steady state problem, so this is 0. So we only have ins and outs. So who's the energy going in? The energy going in is, okay, firstly, we have conduction going inwards into the slice. So Q of x. Then who's escaping the control volume? Okay, so we have Q convection and Q of x plus dx. So we have to subtract away Q of x plus dx, and then subtract again the convection. Okay, so now let's simplify this. So what do we do about this? Q of x plus dx. This is given by the small approximate change formula which we learned in A-maths. Okay, in A-maths, we learned the small approximate change formula, which is this. Okay, so this is given by Q of x plus dq dx multiplied by delta x. Okay, I hope you recall this from A-maths. Yeah, this is a small approximate change formula. Yeah, so we will substitute this into here. So we substitute this into here. And what about convection? So let me just take out my script. Okay, so convection is given by the formula HA. Okay, so what is this? This slice, right? This slice happens at the coordinate x. So this temperature will be at T of x, right? So this will be T of x, then minus the heat will go to the ambient temperature, T infinity. So that's why this will be T infinity. Great. We're not done yet. Now we need to know what's this area. Okay. Now, you see, we're taking this slice, right? We're taking this slice. If you look at it from an isometric view, so let me just draw it out. The slice actually looks like this. Uh, right? This is the slice. The thickness is delta x. Okay. So how do you calculate this area? Okay, so this area is given by the perimeter. Okay, the perimeter times the thickness. Okay, I hope you know that. It's the perimeter, which is how long this whole thing is, times the thickness. And then the perimeter is given by, that's the circumference, right? So the perimeter here is the circumference, so which is pi times d. Oh wait, let's just keep it generic. Let's just keep it as perimeter, because this shape may not be a circle. This shape may not be a circle. It could be a square. Yeah, it could be a square cross section. Okay, so just leave it as perimeter, not circumference. Okay, then we solve it in here. Okay, so now let's put everything into the energy balance equation. So we have first our Q of x, subtract away this one, then subtract away this. Okay, now let's start simplifying this. So this negative can expand to here and here, right? So if I expand that, this will become minus and minus. Then take a look at this. At the front, these two can cancel, right? Qx minus Qx will become 0. Then what about here? Now, what we're left is, are these terms. Copy, paste. Then you see, all the terms have delta x. So I can actually drop delta x, meaning to say I divide every term throughout by delta x so that I can get rid of them. So this cancels with this cancels with this, and then 0 divided by delta x is just 0. Okay? What else do I need to do? This Q, because it's conduction, what I'll use is I'll replace it with the formula from Fourier's law. Okay? Remember, Fourier's law states that Q is given by minus k a dt dx, right? So this, I'll replace it with this, then I'll substitute this in. Minus Okay, let's simplify more. This and this can cancel. Okay, then I'm going to take out these two because they are constants, so Ka, and then the derivative, I'll change it into a second derivative. Okay, then here's the trick we're going to do. What we're going to do is let this term be theta. So theta equals to t of x minus t infinity. So wherever we see t of x minus t infinity, we're going to replace it with theta. Why do we do this? So that we can reduce the number of terms that we see. See, these are two terms, but then if I change it to theta, there's only one term, right? Theta is only a single term. But then if I leave it as tx minus t infinity, then there's a lot of terms. Okay, so this helps us to reduce the terms. So let me show you what I mean. Also, look at this. There's also a t here. Okay, so how do we replace this t in terms of theta? Okay, so here's the trick. Here's the trick. So what we do is we differentiate both sides of this equation with respect to x. So d dx, d dx. So this side is theta. This side is t of x minus t infinity. Okay, so this side, just leave it be. This side, differentiation of this is dt dx, right? Differentiation of this is just a constant. It is a constant. And then differentiation of a constant is just 0, right? Like, for example, differentiation of, let's say, a constant which is 5 is equal to 0. Okay, so differentiation of a constant is just 0. So this will just disappear. Okay, so this will be just 0. Aha, so we're one step closer. So how do I get the second derivative? I just differentiate again. So d dx, d dx. Then this will become d squared theta dx squared, d squared theta, d squared t dx squared. Ah, so take a look at this conclusion. This says wherever I see d squared t dx squared, I can replace it with d squared theta dx squared. Okay, so let's take a look. This thing I can replace it with d squared theta dx squared. Okay, so let's go ahead and do that. So I'm going to replace this with theta. I'm going to replace this with this. Okay, so what I'll get at the end of the day is Ka d squared theta dx squared minus HP, right? Let me check. Yeah, theta equals 0. Then what I'm going to do is divide each term by Ka. So I'm left with this. So here's the trick to getting m to getting the formula for m. So what we do is let this coefficient be m squared. Why m squared? This is to help us reduce the number of squares and square roots later on. You may not understand this, but don't worry, just take my word for it. Just let this coefficient be m squared. Okay, then so if you let this be m squared, then you move the square to the other side, so it becomes square root. Ta-da! Okay, so this is how you do it for the normal thing. So let me recap what we're doing. Okay, so what we do is we take a slice. Okay, we take an infinitesimal slice. Then we consider them the heat transfer. So conduction going in, conduction going out, convection going out. Do the energy balance. Then replace this one with the small approximate change. Replace Q convect with the formula. Okay, then we can get rid of this qx. Then we can drop away the delta x. Okay, drop away the delta x. Then we let theta be, this complicated term here, t of x minus t infinity. Differentiate both sides twice. then we can tell, d squared t dx squared is the same as d squared theta dx squared. Okay, do the replacement, and then divide everything by Ka, and then let this coefficient be m squared. Ta-da! This is how we get our m. We're gonna do the same thing with the hollow cylinder. So let me show you what I mean. Okay, so this is a SolidWorks model of the hollow cylinder, which I sliced out already. So what we're gonna do is, for the hollow cylinder, we're still gonna take a slice. Okay, we're gonna still take a slice. So what I'm gonna do is, okay, so this is the hollow cylinder. Take a slice of it, and then I'm gonna consider the energy balance in this. So this diagram that I draw, basically I'm looking at here. Okay, in case you cannot understand what I'm doing. Okay, so I'm putting my eye like this. Okay, and I'm looking at the slice. Okay, so that's what I'm doing. I'm looking into the slice like that. So again, let's consider the energy balance. So there is conduction going into this phase, conduction going out of this phase. Then let's take a look at the convection. Remember, the convection here is at H out, but the convection here is at H in. Okay, so there's convection here, and then there's a different convection here. Okay, they're not the same because their heat transfer coefficient is different. Okay, so let's go ahead and do the energy balance. Okay, I'm gonna get rid of this image. So again, steady state, so this is 0. There's no more energy being generated. So who's the one going in? There's conduction going in, so this is Q of x. So let me label this. This is Q of x. Then this happens at Q of x plus delta x. Yeah, this is delta x. Okay. And also there's convection going out. So yeah, let's just collectively call this convection first. Okay. So remember this Q of x plus dx, use the small approximate change, which is this, plus dq dx delta x. And what about convection? So remember, convection, there are two components. The convection on the outside. So the convection on the outside is given by, okay, H out. Now, what's the area? Okay, let's just write area out first. So this occurs at T of x minus, yeah. Okay, so remember, this temperature, this position is at the position x. So this temperature will be T of x. And then it goes out to the ambient temperature. So that's why Tx minus T infinity. Okay. Then don't forget the inner convection. So inside there's also convection, right? So this convection will be given by Hi, and then the internal area times the, again, the same thing. Okay. So this is still at the position x. So that's why it's T of x minus the ambient temperature. Okay. Let's see how we can simplify this. So what is the outer area? The outer area, let me just take this again. Okay, never mind. So let me draw the slice. The outer area is this one. So this is A outer, which is given by the outer perimeter, right? This is the outer perimeter multiplied by this delta x. So this is given by the outer perimeter, which is the outer circumference times delta x. Okay. Likewise, the inner area, so inside. Okay, so I'm referring to this. is this. So the inner area is given by the perimeter, which is the circumference. Okay, the inner circumference times, again, delta x, because this is still delta x. Okay, so now we're going to do the replacement accordingly. So, okay, what else am I going to do? I'm going to factorize out this. Okay, I'm going to factorize out this. Okay, h out a out plus h I a I. Put this in one bracket, and then I'm going to factorize that out because they're common in this term and this term, right? So I factorize it out. Then I'm going to replace the a out and a in. So h out is p out times delta x plus h I p I times delta x. Okay, and then do you notice there's still a common term? See, there's delta x here, there's delta x here. So I'm just gonna factorize it out again. Okay, so factorize. Okay, let me just copy this. Okay, factorize this out. Factorize this out. Then you should get a delta x on the outside. Right? So don't forget this is our Q convection. So we're gonna take this, we're gonna take our this one also, put it back into the energy balance equation. Okay, now we're gonna put it back in the energy balance equation. So let me just write down the whole energy balance again. So we have this minus away the second convection, minus away, minus away the second conduction and then the convection. Okay, so this minus away this minus dq dx delta x, then minus away this convection term. Okay, so this whole thing delta x h out p out plus h I p I t of x minus t infinity equals to 0. Okay, so this cancels with this, and then see, you can divide everything by delta x. So this cancels with this cancels with this. Then you replace this with Fourier's law. Okay, so d dx minus ka dt dx minus, okay, so h out p out plus h I p I t of x minus t infinity. Okay, let's see what else we can simplify. We can cut this, cut this. Okay, now we're gonna do that trick where we let this be theta. So if theta is equal to t of x minus t infinity, then differentiating both sides. So this will tell us d theta dx is equal to, so this differentiate dt dx, then this differentiate, this is just a constant, so it becomes 0. Okay, so yeah, it tells us this. And then we're gonna replace this into here. Okay, so that means dt dx, we can replace it with d theta dx. Okay, this k and a, I'm gonna take it out. Then this will differentiate this, right? So it becomes d squared dx squared. And then don't forget, I can just change this directly into theta. Okay, minus h naught p naught plus h I p I t of x minus t infinity equals 0. Oh wait, don't forget, I already replaced this with theta. Okay, then what do? You divide throughout by Ka. This cancels with this. Then what we're left with is this. H naught P naught plus H I P I over Ka. Then what do? We let this coefficient be m squared. Okay? So if m squared equals to this whole term, meaning to say m will be given by square root of h naught p naught plus hi pi divided by ka. Okay, all right. So we are almost there. So now it's time to just substitute in the values. So they told us h naught is 10. Then what is p out? P out is the outer circumference, right? So if you do this, it will be pi times diameter. The outer diameter is 0.02 meters plus hi is 2, then pi times d divided by the conductivity they give us. And then, okay, this area, right, is the cross-section area of the fin. Remember, this is a hollow fin, right? So this is a cross-section area, which is given by this. Okay, so it is the difference of two circles. It's the difference of two circles. So we have pi d squared over 4 minus a smaller pi d squared over 4. So pi d squared over 4. Okay, pi over 4 d squared. Okay, punch this into your calculator and you should get 71.44. Okay? Now, let's see. What's the question? What did they ask? Show that this is a long fin. Okay, so how do we show that this is a long fin? To show that there's a long fin, right? Remember, we need to calculate m times L. Okay, we need to calculate m times L. So let's go ahead and do that. So this m is from here, so 71.44. And then L is the length of the fin. And they told us the length of the fin is, if you convert it to meters, is 0.07. Okay, 7 cm. So if you calculate this, this will be 5.00. And then now ask yourself, is this greater than 2.65? Yes, it's greater than 2.65. Is it greater than 4.6? Yes, it's greater than 4.6. So that means you can use both the formulas for this and this. So, in conclusion, since this is greater than 4.6, which is definitely greater than 2.65 also, that means long fin approximation is valid. Okay, so the answer is yes, we can approximate this as a long fin. Okay, let's move on to the next question. What is the distance from the base of the handle where the handle temperature is 30 degrees Celsius? Okay, what is the distance from the base of the handle? Okay, so this is the base of the handle here, where the handle temperature is 30 degrees Celsius. Okay, so what is this question trying to ask us? Okay, so let me rephrase this question mathematically. Okay, so this question is trying to say, find x such that T of x is equal to 30 degrees Celsius. Okay, 30 degrees Celsius. Okay, remember that we already conclude that long fin approximation is valid. So that means if you go back up, we are allowed to use these two formulas. Okay, we are allowed to use these two formulas. And yeah, I'm gonna go ahead and use that. Okay. Okay. So the formula we will use is this. So we use formula theta b e to the minus x. Okay, this is the first formula, but then I rearrange it. Okay, I rearranged it. Okay. Now they give us temperature, but they didn't give us theta. So we need to calculate theta ourselves. Remember, theta is given by T of x minus T infinity. Okay. They told us that T infinity, okay, if you read the question, they say T infinity is given by 15 degrees Celsius. Okay, that's the ambient temperature in this problem. So they want 30 degrees Celsius, right? So you put 30 here minus the ambient temperature. So this will be 15. Okay. So using this formula, theta equals to theta b e to the minus mx. This, I'm going to replace it with this 15. So 15 equals to this theta b. Okay, theta b is given by what? Okay, theta b is given by tb minus t infinity. Okay, TB is, they said the base temperature is 50 degrees Celsius, minus away 15. So this should be 35. Okay, so theta B, I'm going to replace it with 35. E to the minus, okay, M is the one we calculated before, right? It's this one. So 71.44. So this is 71.44 times x. Okay, so now we're going to solve for x. So put ln on both sides. Sorry. Let me not put ln on both sides. What I'm going to do is move this 35 to the other side. So it becomes 15 over 35. E to the negative 71.44. Then I'm going to put ln on both sides. If I put ln on both sides, then I can bring this 71.44 down. Okay, negative 71.44 x ln e. Ln e is just 1, so this can disappear. So x will be given by ln 15 over 35 divided by negative 71.44, which is about 0.01186. This is in meters, right? So if you change it to centimeters, it'll be 1.2 cm, right? You just multiply by 100 to change it to centimeters. Yeah, done. Okay, next question. What did they ask? The instantaneous heat transfer rate through the base of the handle. So they're asking us to find the heat transfer rate refers to Q dot. Okay, so you just directly use the formula in the infinite long fin formula. So use the formula Q fin is equal to, okay, HPKAC times, okay. No, in the lecture notes, they put theta at the back here, but I don't like to do that. I usually put theta in the front. Why do I do that? Because if I put theta at the back, right, sometimes I might think that it's inside the square root, which is wrong, okay? The theta is outside the square root. That's why I like to put it in the front, so that I know clearly for sure it's not inside the square root. Okay, so theta b, we already calculated, right? Theta b is given by 15 minus 50 minus 15. Okay, tb minus t infinity, which is 35 square root of, okay, what is HP in this case? Let's go back up to the formula that we derived. Do you remember in the normal case, M is equal to square root of HP over KA. So let's draw similarities between these two. Okay, the KA is the same. So the HP here refers to this numerator. Okay, so instead of HP, we're gonna use this expression. Okay, so instead of HP, we're gonna write this plus this. Okay, I hope you understand that. Then you just substitute in all the formulas. I mean, substitute in all the values. So this is pi times d, conductivity, then the cross-section area. Okay, this should be 0.35 watts. Okay? Okay, so it's as simple as that. So what this whole question is trying to do, right, is first help us find M. Okay? After we find M times L. Then we check the criteria for infinitely long fins. So since the value is 5 is greater than 4.6 and is also greater than 2.65. So that means we can use the long fin formulas. So we use the long fin formulas to first find the value of x at which the fin temperature is 30 degrees Celsius. And we also use the long fin formula to find the heat transfer rate through the fin. Okay, now let's go to question 5. Okay. In question 5, let's read the problem. 2 3-meter long and 0.4 cm thick cast iron steam pipes of outer diameter 10 centimeter. Okay, I'll start with these flanges. Okay, this is the flanges. Okay, and then they're given these dimensions. Okay, so inside this steam pipe, there's a convection going on with H as 180. Yeah, and it has a temperature of 200 degrees Celsius. Okay, then outside, there's still convection going on with H as 25 and ambient temperature as 8 degrees Celsius. Okay, so disregarding the flanges, so that means you ignore the flanges. Okay, disregarding means ignore. So imagine the flanges are not there. Determine the average outer surface temperature of the pipe. Okay, so what we will use in this case is thermal circuits. Okay, so let's look at the cross section of the pipe. So remember, inside here is 200 degrees Celsius. We have a heat transfer coefficient of what? 180. Okay, so there's some convective resistance going on in here. Then through the wall, there's conductive resistance. Then through the wall into the ambient temperature again, there is convective resistance. Okay, so let me label this. So the convective resistance is 1 over H naught, and then the inner area, so let me just call this A1. Then this is the conductive resistance given by ln R2 over R1 divided by 2 pi KL. Okay. And then this convective resistance, which is given by H. Wait a minute. Hold up, hold up. This is supposed to be outer. Sorry, this is supposed to be inner. HI. Then this will be HO. Then this A2. Yeah. Okay. Yeah. So we're gonna use this to calculate the calculate this temperature TO. Okay, so how are we gonna do that? So what we're gonna do is we are going to use Kirchhoff's current law. Kirchhoff's current law. Okay, so pretend this is a node. So we take Kirchhoff's current law at the node TO. Kirchhoff's current law says that the sum of currents entering the node is equal to the sum of currents leaving the node. So in heat transfer, currents correspond to heat transfer rate. So Q in is equal to Q out. Now let's say heat is going into this node. Let me get my red pen out. So heat is going into this node and then out of this node. So let's look at Q in. Q in is from here to here. Okay. So remember, we're going to use Ohm's law. So in this case, Ohm's law is given by delta T over R, right? Then this is T start minus Tn. So this current starts from 200, ends at T naught. Okay. 200 minus T naught divided by what's the total resistance? So we have the convective resistance plus the conductive resistance. So ln R2 over R1 divided by 2 pi KL equals to, okay, now the H out. Okay, so H out, it starts from here. So it starts at T out and it ends at here, which is the other temperature. Okay, let's not call this T out. Let's call this T infinity. Okay, this is T infinity. Okay, it starts at T out, it ends at T infinity. So it starts at here, ends at here. Then the only resistance is the convective resistance. Okay, so now let's substitute in the values. So this, wait, I'm using pi dl. Okay, pi dl. This area, right, is given by this area. It is referring to this area, which is given by pi dl. Okay, so pi times this diameter times L plus ln, okay, the outer radius divided by inner radius, 2 pi it is the conductivity times the length. Okay, so you see in the denominator, right, all of them have a factor of L. So we're gonna cancel this already. All of them have a factor of L. And your only unknown is T naught in this case. Yeah, so you go ahead and solve this yourself. Okay, slowly solve this yourself to find T naught. At the end of the day, you should get 174.5 degrees Celsius, which is close enough to the answer. Okay, I know it's 174.7, but then it's close enough. Okay, so now using this temperature for the base and then treating the flanges as fins, determine the efficiency and the heat transfer rate. So what they're saying is, okay, now that we know TB is equal to 174.5, calculate, okay, so find the efficiency and the efficiency of the fin and the heat transfer rate of the fin. Okay. Okay. So this is a standard procedure to solve this kind of problem. This kind of standard fin problems. Okay, standard fin problems. So let me outline to you what's the steps. Okay. So how to calculate Q fin using efficiency. Okay. So the steps is this. Number one, find find theta using the eta versus psi graphs in textbook. Then number two, what you do is okay, you calculate Q max using this TB minus this. Okay, so you calculate this. Let me make this more clear. Calculate. And then finally, calculate Q fin is equal to eta times Q fin max. Okay, remember we went through this already? This actually comes from eta is equal to Q fin divided by Q fin max. But then I just rearrange to make Q fin the subject. Okay, because normally we want to find Q fin. Okay, so let me say what's the procedure again. Okay, so you open your textbook, you go to those familiar graphs. Okay, you select the correct graph, which depends on the fin type, right? So like sometimes it can be parabolic fin, triangular fin, or this the circular kind of fin, whatever. Okay, and then you find eta using the eta versus the psi. Okay, this Greek letter is called psi. Yeah, psi. Okay, so you find eta, and then after that you calculate Q fin max. Okay, Q fin max is given by this formula. So h times the area of the fin times TB minus T infinity. Then calculate Q fin, which is given by okay. This eta comes from step one. this Qfin max comes from step 2. Okay, so step 1 and step 2, you multiply the answers together to help you get the Qfin. Okay, so this is how you do it. Find eta, calculate Qfin max, then take these two answers, multiply them together, you get Qfin. Okay, so let's have a look at this problem. Okay, so using this temperature, calculate the efficiency, determine the efficiency. Okay. Determine the efficiency. Okay, so I already have the graph here. So basically, you open your textbook, then you get the right graph. So this is the graph that I want. Okay, let's have a look at this graph. When you open your book, see, you'll find this graph, and it tells you to calculate this. So, of course, you cannot remember this. So you just follow what they say. So they say psi is given by LC 3/2, then square root. Okay, this to the power of half is just square root h over k AP. Okay, so what you do is you fill in the information that they want. Let's see what values do they want. Let's see, they want okay, let's see what's R2. Okay, let's go back to our graph. I mean our diagram. Where's our diagram? Okay, here. Okay, so let's have a look. R2, right, refers to this whole thing, which is 10 centimeter, right? So, see, this is 20. 20 divided by 2, this is 10 centimeters. 10 centimeters is 0.1 meter. Okay, so we know R2 is 0.1. Then what else? Okay, the thickness is given by this, which is 2 centimeters in total. So thickness is 0.02 meters. Okay, this is 2 centimeters. Then what else? So now we can calculate R2C, right? Which you just follow this formula that they give you. So R2C is given by 0.1 plus the thickness divided by 2, and this should be 0.11, right? Then what else? We need to calculate LC, right? This next thing they want is LC. So LC is given by, now what is L? L is given by this distance to this distance, which is the same as this distance to this distance. Okay, so this and this are the same. So how do you get that? You take 20, this 20, minus away this 10, divided by 2. Okay, 20 minus 10 is 10. 10 divided by 2 is 5. So each side is 5 cm. 5 cm is 0.05. Okay, 0.05. Okay, so L is 0.05. LC will be this plus the thickness divided by 2. Then this will be 0.06. Then next we want to find AP. Okay, they give us AP here. So AP is given by LC times T. So the LC you take it from here. The thickness is the 2 centimeters. And this should be 0.0012. Okay, so after you calculate all these values, now we can find psi. Okay, so do we have LC? Yes, we already calculated LC here, which is 0.06. 0.06 Then our H is what? They told us H is 25. Okay, they told us H is 25. Then K, they told us it is 52. Then what's AP? AP we already calculated, right? Down here. We calculate AP. This is 0.0012. Okay. Put this in your calculator. You should get psi will be what? 0.294. Okay. And then you see which curve do we use? So to select the curve, right, we need to calculate R to this ratio. Okay, this ratio. So here, 0.11 divided by R1. So R1 is given by 5 centimeters, okay? It is given by half of this, so this is 5 centimeters. Okay, you calculate this, it should be about 2, okay? It's about 2. So so you're gonna focus on this graph, the one that's labeled 2, okay? Because the ratio is 2. Okay, and then you go to the Kasai. The Kasai they give you is 0.294, right? Which let's say is about 0.3, right? This is very close to 0.3 already. It's very close to 0.3. So you go to 0.3. Okay, 0.3 is midway between 0.2 and 0.4. So you're over here, you go up, and then you hit the 0.2 graph. Okay, and then you go to this side. There, you can find your efficiency. Now, don't ask me why this efficiency they give, right, is uh 0.88. Yeah, I don't know. There's some inaccuracies in reading this, okay? So let's just follow what the answer give us, 0.88. But this is essentially the idea, okay? So don't worry about the accuracy for now, okay? So what you're supposed to do is calculate everything they ask you to calculate. Then using this, you calculate Kasai. Then from Kasai, then after that, you calculate this ratio. The ratio helps you select the curve, okay? You select the curve, and then uh the Kasai, you go to that value. So you go up and then go across, then you find your efficiency. This is the idea. I don't know why it's a bit inaccurate. Yeah. So they say it's 0.88. Let's just stick with it, okay? For agreement's sake. I'll just stop for a while.